Hey Shane.
Hey, how are you?
Sorry, I don't know. I got so bombarded. I joined a new class a week late. And
Uh-huh.
so yesterday was insane. Well, yeah, yesterday.
Got it. What
But
class are you taking?
what?
What class are you taking?
So basically to graduate, I needed a communications credit and they wouldn't let me into the communications class. They said that it was closed and only for the majors. And I was like, well, that's stupid. Why is it my requirement?
Mm-hmm.
So 34 emails later, I finally got let in, and there was apparently an essay due on Friday.
Mm-hmm.
I had to get done. Yeah, they said I had to submit.
Is that a requirement for your school or
I had to graduate.
got it?
How stupid. They're like, the
Yeah.
school requires it, and they wouldn't let me in.
Yeah. All right, cool. All right. Yeah, let's go over that test.
So how do we go over it? Like, should I? Well, here, I'll share it.
Mm-hmm.
Um,
Mm-hmm.
yeah. What does it say?
Yeah, you're gonna have to hit next. That's like the downside of this, but uh yeah.
Okay, so then, fucking remember. Stop. Should we do this one?
Mm-hmm.
Yes, I remember we did this. And see. Yes, we did this. This. Yes, I remember.
Mm-hmm. Yep.
I remember explain this. Talked about this one. Do we stop here?
I think so. I think we skipped this and did some more discretes, but yeah.
All
Uh
right.
let's do this. So okay, let's see. Researchers used reverse phase high performance liquid chromatography HPLC with a polar mobile phase and nonpolar stationary phase to separate compound 2 from compound 1. Which statement accurately describes this process? Okay, let's see. So compound 1, compound 2. What's the difference?
This
Yep, and what's that?
H3CO. I don't know.
Um, try it out.
Okay. Imagine a carbon with a hydrogen here, and
Okay.
then the oxygen double, which is linked to two hydrogens.
Is it linked to 2? Because that CH2 part,
Oh,
okay. And now what about this one?
well,
Yep. Your favorite group, the OH group, the hydroxyl group.
mhm.
So okay. Now, what is this, what like, what is this like in terms of polarity? Is it polar? Is it non-polar?
Isn't OH usually negatively charged?
Well, uh
Or no,
think
that's
about uh if it's polar or not polar. Like polar would mean partial charges. So yeah, would this be polar or non-polar?
overall, or I think they cancel each other out and it's overall non-polar.
Uh, well, the oxygen is
The
elect
only time I remember seeing CH2 is like CH2SO4.
um you mean H2SO4?
Maybe, yeah.
The CH2 just means that that's a carbon. Like, like you could write this like I'm going to draw a squiggle here to then show that it's like this, right? Where this is just CH2. I mean, it's CH2 because one of the carbons is
Because
bound
there's
here and the other one's bound there.
perfect.
So that's just like an alcohol group, right?
Uh-huh.
Now, the question is that a polar or nonpolar?
Um, how do I figure that out from just looking at this?
You can think about electronegativity.
Well, O is electronegative
Yep. So it's going to pull electron density.
towards the
Or,
O. And then since there's no double bond, it has to be polar, right?
yeah,
Or
yeah.
would it be resonance stabilized?
Yeah. So I mean, if it was like a double bonded oxygen, it would still be polar.
Uh-huh.
Right. But yeah, it's polar. It's you have that electronegative oxygen group, part of that, um the hydroxyl group. So yeah, it can also participate in hydrogen bonds and stuff, right? So compound 2 is more polar than compound 1. So it would be the opposite of this, right?
So compound 2 is more polar.
Yep.
So it will elute first, which is, hold on, I'm doing the annotate thing.
Yeah.
It's just D. Makes sense.
Yep. Elute first because it does not interact with the stationary phase, which they told us was nonpolar. Okay.
Okay. Yeah.
If you forget, you could also remember STY.
Yes. But what does STY have to do with
So STY are
the polar,
yeah,
right?
polar amino acids, right? And they all have that hydroxyl group.
Okay.
Yeah. Okay.
Yeah.
Mm-hmm.
I just looked at that table. I got this one right too. And that one. Wait. Oh yeah, I mean it's getting reduced. It's losing an electron, which makes it gain a positive charge. So yeah.
Yeah. Wait a
Which
sec.
I thought,
Did you say it was getting reduced or?
well, it's not getting oxidized because it's losing an electron. Oh, wait. Oops. Yes, it's losing an electron, it's getting oxidized.
Uh-huh.
But the reducing agent, and this is the
Reducing agent would reduce other things and itself get oxidized, right?
okay.
Yep.
Here I was confused because it literally switches, right? Like it's HCl and Mg, and then it's MgClH2. So I thought it was a double replacement. But
Oh, well, it could be like, so I see that the Cl can go to the Mg. So that's a single replacement, but it's not like the Mg is,
and to the H2, I understand.
yeah.
Okay,
So
that's a single replacement, not a double replacement.
yeah, and so what you want to do with these is uh write out the oxidation states for each. So magnesium solid is oxidation state of 0. H2 gas, oxidation state of 0. Now, HCl here, the Cl has a -1 oxidation state, and then the hydrogen has positive one.
Mm-hmm.
Here, or rather here, we have two Cl's, so that'll be 2 times -1, which is -2, and the magnesium would therefore have to be +2, right? So the magnesium goes from a charge or oxidation state of 0 to +2, which means that it's getting oxidized because it's losing electrons, right?
Mm-hmm.
And the HCl, the hydrogen at least, goes from +1 to 0, which means it's gaining electrons.
Electrodes, so that's the oxidation and the reduction. I understand.
Yeah, so the H gets reduced because it's gaining electrons, and the magnesium is getting oxidized because it's losing electrons.
Okay. But Lewis acid and Lewis base is proton donor and electron donor and electron acceptor.
Oh,
So, but in order for that to happen, it has to be oxidized, right? That's
so
the
the
thing.
Lewis base would be the electron pair donor.
Uh-huh.
Lewis acid would be the electron pair acceptor,
Yeah.
right? But uh, the I guess what they're showing us here is that um is just that yeah, I mean, if there is some type of Lewis base or something, that would like typically like be like a nucleophile and would result in like a nucleophilic kind of, substitution, like SN1, SN2 or something like that. But here it doesn't seem like that's happening. It doesn't seem like, you know, anything's donating a lone pair, right? All we see that's happening is that the oxidation states are changing.
Okay.
So whenever the oxidation states change, we know that it's a redox reaction.
Yeah, no, I understand why the answer here is. I just kind of wanted an explanation why it's not B.
Mhm.
Okay.
Yeah. Yeah, because there's no nucleophile stuff happening.
You got this right? Yeah. Um, I can't remember. I like tried to think of this from the like what we talked about this before, and I guess it worked out. So yeah.
Um,
Talking about pressure.
mhm.
Yeah. Okay.
Yeah.
Did I get this right or wrong? No, wrong. Because isn't this the equation?
They're asking you to calculate the gas constant. So right away we can get rid of that and that.
Gas constant is R.
Mhm.
Okay. Because I know when you're solving it, I feel like N R are always constant, right? So
N
you
would be the number of moles, so that can change. Um,
R.
but R is the constant. There's two two versions of that constant, like with different units. Like it
Mhm.
can be like 8.3 or it can be 08.08. So this is joules over moles times Kelvin. This is liter times APM over moles Kelvin.
Okay.
Mhm. So yeah, they're asking you how should the ideal gas equation be rearranged, right? To calculate the gas constant.
So you just
So
have to isolate R.
yeah, but even if you didn't
Is
understand.
it you delete NT on both sides? Sorry, divide.
So yeah, even if you didn't get that aspect of it from the question stem, it does say that it's how would it be rearranged. So we know
Okay.
that it can't be this because that's not how that's how it is before you rearrange it.
Right. Okay.
Yeah. All right. The goal of the experiment
Can we answer this without reading through it? Do you know these passages? I feel like you've taught them a million times.
I mean, like, I would still read.
Read through it.
I don't like place an importance on like the like remembering the stuff. Um,
Right.
because I
Yeah.
think it's better to
Approach it with fresh eyes every time.
yeah. I mean, like even though I've seen a bunch of these, but yeah, if they're asking what the goal of the experiment is, let's see what they say when they say that they're doing the experiment, right? So they said that um the ideal gas constant, wait, let's see. Magnesium ribbon, blah blah blah. There's nothing below this. Okay. So I guess they're just saying that the ideal gas constant R could be found by measuring the volume that a given amount of gas occupies at a certain temperature and pressure. So one technique for accomplishing this is to react a known amount of magnesium with acid to produce hydrogen gas. And then they do a bunch of other stuff about that. And
Right, but isn't that whole thing just talking about this reaction and then they're using these tools to test out the reaction?
so mechanism is when you do like the arrow pushing stuff. So so yeah. So it's not going to be a mechanism thing, right?
Uh-huh.
So like like how let's say this typical example here of like this attacking that.
Yeah.
Like how do we know that's how it works, right? Because maybe you can have some alcohol and then have some ketone. Like let's say you mix like literally like ethanol alcohol with like acetone nail polish remover, and then you get, I don't know, like a carboxylic acid perhaps. That can at least that'll show you that if you just add an alcohol to a ketone or an aldehyde, that you end up with, let's say, a carboxylic acid. But how do we know if that it's like the hydroxyl group attacking that carbonyl carbon, right? And that's something that you find out through like labeling. Like you could label the oxygen isotope and see if it's, you could label the one for the alcohol and see if it's in your product of your, acid. But mechanism is that it's like the arrow pushing stuff, like knowing the exact stuff that happens at that, molecular level. Now, so B is I can see it being a tempting answer, but it's not going to be right because of the word mechanism.
Right. That's so annoying that like one word just
Yep, that's how it is on the MCAT, but it's not like, you know, it's not like it's beyond, you got like perfect score in like your car seconds. So, it's not beyond your abilities here. But okay, let's see. So evaluate the molar mass of H2 gas. So I know they talked about the different readings of the volume of the gas, but they never did anything with molar mass, right? Um, and then we have the reactivity of magnesium with acids. I mean, they're talking about in this first paragraph how the ideal gas constant relates to these four parameters, PV, N, and T. And then they did, ideal gas constant can be found by doing this experiment. So the experiment seems to be to find the relationship between R and then the four parameters, PV, N, and T. So C would work there.
I get it.
Yeah, experiment as a way to calculate the ideal gas constant R using other measured variables, such as volume, temperature, and pressure. It's hold on, Lisa. Okay.
I did the math.
They give us our
There, I threw out my
what's
the
up?
paper. I like I did the math, but I threw out the
Oh yeah,
paper.
you're just off by a factor of 10.
Oh. I did
Mm-hmm.
the E conversion, like the way we did for meters cubed.
Mm-hmm.
Meters cubed, and since it's already cubed, it's only E to the third, right?
Yeah, let's see. Because so we know from before, I don't know if you remember, but one cubic
Equals
meter would
6.
be 1e6 cubic centimeters.
Right. Yes.
So let's see. So they're talking about the density 1060 over cubic meters and 1060 kilograms over cubic meters. And they're saying that 1 liter consists of 1000 cubic centimeters. So
Mm-hmm.
I can do like what I did here, but put the 1000 in the front. So this should be 1000 uh E6. Um oh well, if I'm converting it into so I'm gonna just do this. So 1e-6 cubic meters is equal to 1 cubic centimeter.
Yeah.
So like so yeah, since I'm gonna convert it into from cubic centimeter into cubic meter, I'm gonna
Just
just do that. So I'm gonna put E-6 cubic meters, and then we have 5 liters of blood. So this will just be, well, I guess I can do like 1E3 for the 1060 times 1E, so left subtract, right add. So 1E, moving it over, I'm moving the decimal point of the 1000 to the left 3 times. So I'm adding 3 on the right to get 1E -3.
mm-hmm.
Then times the 5. So this should give me 5E. Wait a sec. Let me make sure I'm doing this right. 1E3 kilograms. And then left subtract, right add. And if I'm doing E-6 plus 3, should be E-3. So I'm getting just, oh, well, you know what? No, that works then, because the E is 0. So that's just 5.
Which is the answer.
Yeah.
Yeah.
I think yeah, this is just like making it like it's just off by a
Oh,
factor of 10.
yeah. I
So
wish I still had the paper to know how I did that.
mhm.
Okay, so I was really confused with this one because I was trying to think of like
Mhm.
um Doppler. Like I remember the way that like they do the ultrasound is different and you hear the heartbeat.
Mhm.
like I don't know, there's like, anyways, so I picked C, that you needed to like have the moving object inside, not just the sound of the. I guess this doesn't really make sense, my answer, because what is the speed of the moving object? But I guess relative to the sound so that you know it's like being heard over the blood,
Mm-hmm.
like pushing.
Yeah, let me see the question again. An ultrasound examination could show the motion of a fetus. In order to image this motion, the ultrasound examination devices require what
Minimal
minimal
information. I guess I didn't finish reading.
okay.
So the sound and frequency are the minimal information. And then this would be like an additional fact that you have.
Um, yeah, I think that that you can like figure this part out from just this and the frequency like difference between what's emitted and what's observed.
Yeah.
So,
Okay. Wait. Oh, I got it right. Yes. It's because of electronegativity, right? Like, why is it that hydrogen bonding
remember Fawn?
H on the phone? Yeah,
Yeah, hydrogen bonding can happen between like hydrogen and then F or O or N.
got it. Yes.
So
Sounds.
FHF can have really good or strong hydrogen bonding.
Hmm.
And boiling point is all about like the intermolecular forces, right? So if you can break the intermolecular forces, which are hydrogen bonds, then it can boil.
Understood. Okay. Listen, I got it right. I don't. Honestly, I just I was thinking of like what ibuprofen is and like how it acts, and it didn't make sense to me that ATP, glucose, or glycerol would act in the same way.
All right, tell me a little bit more about it, about that.
Well, this one's a triphosphate, and this one is, oh, I honestly don't remember now.
Yep. So
Like, so they're talking about hydrophobic parts, I
yeah.
guess.
So for ATP, it has the
Hydrophobic with anionic.
what's up?
Sorry.
Oh, so I mean, okay, so first of all, let's take a look at ibuprofen. So we want to be able to tell what happens here from looking at the functional groups, right? And so we have a benzene, which is going to be nonpolar, right?
Right.
Then we have what is this?
Hydrox. So
I knew you were gonna say that. No, something else.
what is this? What ends with OH?
Yeah, remember, know all of the things that have that carbonyl group in it. Like,
Yeah.
what is this?
Oh, I spent so much time memorizing them. Why can't I remember?
So if it's just an H,
Uh,
it'll be an aldehyde.
mm-hmm. Ketone is the OH one.
No, so and then if it's
R.
another like, yeah, carbon or something, like our group, let's say, it'll be a ketone.
Yes.
And then if it's, let's say,
OH. What
and
is the other one? NH is an amide.
good, you're good. What about OR?
OR is a. I wish this was a multiple choice. Like I could match them, but when I'm looking at just the picture without the names, I can't remember.
So let's try. So um, it's one of the carboxylic acid derivatives. Starts with an E.
S.
Mhm. That's
Yep.
yep. And then this
Ether. No,
carboxylic acid.
but the carboxylic acid is just this. Or
No,
that's the carbonyl.
yeah. The carbonyl could be
Carbox.
those things, right? It
Okay.
could be aldehydes, ketones, esters, amides, anhydrides. But
Okay.
this, you so think about it like this. If it's an acid, it donates a proton, right?
Yes.
So it will look like this plus H plus, right? Right?
Yeah.
And what's more stable, this on the left or this on the right?
This.
All right, why?
Because the electron has already left. That's why there's the proton.
Yeah, but how does that make it more stable?
I guess not. Wait.
What do we usually say?
Negative charge. Well, when it's there's no charge is when it's most stable. So OH is the carboxylic acid is the one that's more stable
Yeah, but why?
because it's resonance stabilized. There's no charge, but if there was, it could travel along the double bond.
So wait, which one are you saying is more stable?
Double bond could go here and then
Wait, which molecule?
you said this one was wrong, so then I started looking at this one.
No, I didn't say it was wrong. I was saying why.
Well, I think that the negative charge, like when there's a charge, it can travel along. Like it can be resonance stabilized with the
Okay.
structure
Yeah,
of them.
so it can be resonance stabilized.
Yeah.
That,
Okay. All right.
that can go here. This can go there.
Yeah.
That's why it's more stable like this, meaning, it's an acid because if it wasn't an acid, it would be more stable before it gave its proton away. But if it's more stable when it gives its proton away, then it would be an acid, right?
Yeah.
So
Yeah.
remember this over here. Okay.
Hmm.
So, all right. So now if we look at ibuprofen, we have our hydrophobic benzene. And like this aliphatic, like a carbon chain is also going to be hydrophobic. And we have our carboxylic acid part, which is hydrophilic, right?
Yeah.
Yeah. So now they're asking what would bind to the same site as ibuprofen, aka what would be similar to ibuprofen in that it would have like what would have a hydrophobic portion and a hydrophilic portion, right? So like glucose is only going to be considered it's only going to be
That's
um
hydrophobic, right?
uh
Hydrophilic.
yeah, because it has a bunch of hydroxyl groups, your favorite groups,
Mm-hmm.
and stuff like that. ATP is going to be not just polar, but like charged, right? Like if polar is a partial charge, a full-fledged charge will make that even more so polar. So that this doesn't have any hydrophobic portion. Glycerol looks like this. And it's the backbone for fats, for lipids.
Mm-hmm.
Um, so and as you can see, remember what I told you, like right, like a few questions ago, like hydroxyl groups are polar.
Mhm.
So this glycerol is only polar. So we have A, B, and C are all polar, but
Right.
This is a little tough because they I guess expect you to know that this is because we know it's a type of acid, which means that it's a polar, it has a polar part. But I guess it's tough to say like, that this part is like a hydrophobic fat, but it's this is an example of a palmitic of a like a fatty acid.
Okay.
So so you could have solved this with even if you didn't know like specifically that this had a hydrophobic part to it, by knowing that A, B, and C all do not have hydrophobic parts and therefore cannot be the answer. And that comes from being able to look at the molecule here and being able to say, oh, okay, this is nonpolar, hydrophobic. This is hydrophilic.
We do it for the other ones too, like try to figure out the structure. And
Sure. Functional groups, you mean? Yeah.
do you have the benzene rings, which we know are nonpolar? What does this count as? Because I remember seeing, do you remember the problem that it was like
So
a triglyceride, but it wasn't correct, like they were open?
so I drew this earlier. It's, you know, when you just have that R group that
That's okay. So does this count like the carbon is just an R group?
uh-huh.
Okay, so that's a ketone.
Good, 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 good.
This is a hydroxyl group.
Favorite.
And what is this? Just a freestanding.
Just uh
Or no, is that
mhm.
hold on, we looked at one. This is a ester, right?
Yep. And when you have a cyclic ester, it's called a lactone.
Okay. That's cool.
But good job. Yep, it's an ester. And then
Right.
yeah,
This is a carboxylic acid.
yep, yep, yep.
You have one benzene ring.
Hmm.
Um,
Hmm.
is this an R group?
Yeah, this could just be like a cyclic, like
Cyclic.
I don't want to say cyclic
Oh,
ketone, but maybe just like a carbonyl.
okay.
But yeah. And then you have some rings with nitrogens in them.
Right.
So yeah, good job.
Nitrogen is electronegative, so it would be polar.
Oh, which part?
Like the nitrogens, like FON, like they're all electronegative. So overall, this would be a polar structure, right?
So I think since the nitrogens are part of rings,
That it cancels.
that yeah, rings are going to be nonpolar just because of like the symmetry,
Mm.
but it would be able to.
Is it for all rings or when they're called like the aromatic rings that have every other double
Yes,
bond?
like if we had a regular cyclohexane or if we had a benzene, right, they'll be nonpolar. Now, these heterocyclic rings, which mean that they have something other than, you know, um, carbon, they can also have like polar aspects to them, which would enable them to, for instance, hydrogen bond, like there could be a hydrogen bond here, uh, with, something else. So, but yeah, I would say that the ring portions are predominantly nonpolar, carboxylic acid, predominantly polar. And then like, maybe like just these nitrogens could also have some polarity to it. But overall, I would say similar to the ibuprofen, like the rings are the nonpolar ones, and then that high carboxylic acid group would be polar.
Okay.
Mhm.
All right. I I remember this problem. I remember how I
Mhm.
is it because this value? I think so, yeah, right? Because it's already table 2.
Yeah, so they're asking about the binding site of CPFX, and the K naught represents the affinity of CPFX to the BSA.
Right.
And in table 1, we see, okay, warfarin has this affinity, ibuprofen has this affinity, and they're not being nice by just giving us K naught values. They're giving us Ka over K naught values.
To divide.
Uh-huh. So, but that would mean that the larger K naught is, the smaller that number would be, right?
Mhm.
So, uh,
Exactly. Right.
and then they said in the passage that warfarin binds to site 1 and
Mhm.
ibuprofen binds to site 2, right?
All right, so then site 1 for warfarin, the K
Mm-hmm.
naught is greater.
Mm-hmm. Yep.
Cool. I'm gonna assume that this was a guess, but I remember looking at the problem and I'm genuinely unsure.
Mm-hmm.
Oops, what just happened?
I don't see anything different.
My thing closed. Is it only on the Google? It might be. All right. Okay.
Mm-hmm.
How can you figure out most line with which chains? Site 1 and 2.
So, have
Oh,
you,
is this based off of the structure that we figured out for like ibuprofen and warfarin?
so in the passage on the left, if you scroll up, so they're saying that so like the serum albumin, blah blah blah, and then the ligands mainly um hydrophobic with anionic or electronegative features, right?
Mm-hmm.
So that's what the ligands would be. So we want to figure out what can bind to that, right? So for instance,
Okay, so that what hydrophobic would bond.
yep, to the hydrophobic part, and then cationic things would bind to the anionic part, right?
Wait, but why would hydrophobic bind to hydrophobic, but cationic to anionic? Shouldn't it be the opposite for the other one too?
So hydrophobic and hydrophilic refer like operate by in terms of solubility, like dissolves like. So hydrophobic things would be dissolved in hydrophobic solvents, and hydrophilic like solutes can dissolve in hydrophilic solvents. So if we're talking about hydrophobic and hydrophilic, it will be like dissolves like. But if we're talking about something charged, opposites attract,
Mm.
right?
That makes sense.
So you want something that's hydrophobic to bind to the hydrophobic parts of the ligands, and then you want something cationic to bind to the anionic parts of the ligands.
Hydrophobic
Yep.
would be non-polar, right?
Mhm.
And the polar ones are STY.
So those will be some of the polar amino acids.
And
Yep.
then there's also asparagine and glutamine.
Yep. 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 Great job.
And the charged ones
Yep.
were which?
Mhm.
Mm.
That would just be the acidic and basic ones, right?
So acidic is aspartic acid and glutamic acid, and basic is it al histidine, leucine,
I wrote his
al
eyes are.
arginine?
So histidine, lysine, arginine.
Okay, all right. Okay. So histidine, lysine, arginine. Lysine is
Those are the basic ones.
basic.
So what chart
Died.
are they?
Distracting me. I'm
Yeah.
sorry. Wait,
What's up?
what does that mean?
Oh, are you trying to hide it? I think
Yeah,
like that.
but I'm clicking. Do you see the pop-up?
No.
Submit a response to see the solution. Did I unclick my answer? Oh, I guess I didn't answer this.
Okay.
Hide the solution because I don't have an answer.
Got it. Okay. Yeah, so what would like the charge be on like the basic amino acids? Um, and the acidic ones.
Acidic would have a positive charge because it would want to lose an electron, right?
Um, what
Or
do acids do?
acids. Electron donors.
Um,
That's
so if we go back to carboxylic acid, what did that do?
proton donor. Sorry.
So so what charge would so if an acid donates protons, what charge would it be after it's given its proton away?
Positive
What's the charge of a proton?
plus. Oh, so negative.
Yep. And so the basic ones accept protons, so they would be what charge?
Positive.
Hmm.
Okay.
So if you want something to bind with something a ligand that is anionic means negatively charged, right?
Mhm.
And we therefore want something positively charged to bind to that negative charged ligand, right?
Mhm.
So that's why we want a basic amino acid, right?
Yeah.
And so like E is what?
I have no idea which E.
So it'll be glutamic
Ah,
acid.
okay. So it would have a negative charge.
Yep. Which we don't want, right? What
And
about
Y is uh I can't remember if it's threonine or tyrosine. No.
it's at least one of the STYs, which we know are what?
Serine, threonine, and tyrosine.
Yep. And then what do they all have in common?
OH.
Which means that they are,
Well, they're polar.
yep. And we don't want that either, right?
Yes.
That's out. D,
D is aspartic acid. Or
yep.
is that, yeah.
So that's negative. We don't want that. And then E is glutamic acid, which is negative. We don't want that. D again, negative. We don't want that. H, histidine. That's okay, but we the
Not that D that we don't want.
aspartic acid is not going to work, and we want a hydrophobic.
R we said is arginine and leucine.
Yep. Leucine is just a regular non-polar, hydrophobic amino acid, and arginine is a basic amino acid.
Wait.
Yep.
We said that these are the bases.
Yeah, this is lysine.
Oh, leucine. Leucine is in the nonpolar, the first group, right?
Yeah. Lysine has the single letter abbreviation of K.
That's yeah, okay, that I got confused. I know. Okay. All right, sounds good. So A.
Yep. All right, this is some math stuff here. What is the approximate density of the wire at 473 Kelvin? Note the volume of the wire is 5 times 10 to the negative 7 cubic meters again. So great. All right. So let's see. All right. Yeah. How do you approach this?
Okay. Literally I did this. I remember wrote it out on paper. I was like D equals M over V. Or no, D equals yeah, M over V. And then we're given, well, I guess this is where I got confused because there's another equation that I needed here.
Where? Well, which thing?
This one, V equals IT, right?
Well, they give us the mass of the wire, right?
Yes.
And then they give us the density, the volume in the question stem. So it may, yeah, maybe the 473 Kelvin we don't even need, right? We just need mass and over volume to get the density.
I thought that's how I did it though, and that maybe it was like a math error because I
Let's
remember
try.
getting times 10 to the e to the fourth. But wouldn't it be, yeah, I did 4/5 e to the negative fourth. No, e to the fourth. Yes, because -3 plus 7. So it's 4/5 e to the fourth.
-3 plus 7. Are you there?
Me, yeah.
So, you there?
I understand. It must have just been a math error.
Mhm.
Okay.
The relationship between T and R.
hmm
That one made sense.
I
Okay.
got it right.
Yeah. But I'm just wondering,
Yeah. I went off of the data here.
Mhm. Got it.
If you look as it goes up, this goes up.
Mhm.
Um,
This is another off by 10 error, perhaps. Oh, wait.
oh,
Yeah. Yeah.
that's so annoying. I wonder if like I was so excited that I used the right formula and everything.
Yeah. Let's see. Okay, Q equals MCAT, right?
Mhm.
Could be like maybe a unit thing. So let's see. They're saying that the okay amount of heat. What? Okay, so we need the mass, which I guess is the same thing, right? This one. So 4e-3 kilograms times they give us the specific heat, 460 joules per kilogram times Kelvin, and then the delta T is 200 Kelvin. And so we get, I'm going to just write this as 2e2. I'm going to multiply it by the 4e-3 to get 8e-1. And I'm going to multiply that by the 460. I'm just going to write 500 or 5e2 to get 440e 1, which is 400. And since I rounded the 460 up to 500, 400 is the upper bound. So I know that it can't be greater than 400. So these are out. Must be that.
Okay.
So I think you got like something like this to the second power.
I must have, I don't know. Just weird that I got like every other one right for this passage. Did you notice? Okay. During trial 5, the wire was heated. Oh, I got this one right.
Mhm.
I don't remember it.
They said during trial 5, the wire was heated from 293 to 673, while the voltage was held constant. How did the current through the circuit change during this time? Okay.
Wait, I remember this. There was some current is D3 is this one. And so then I was looking at the current from the beginning to here. Wait. But when was the current at 4? There's something I'm missing right now that I was looking at when I was solving it. Because where is the 4.6? I like based on what I'm calculating now, that you're just looking at the current jump from here to here, that it should have been increased to 2A.
Mhm.
That I don't understand where I'm getting the 4.6 amps from.
Um, okay, let me see that top of this again. So okay, voltage 28 volts is equal to, let's see, is that really a current of 0? And this is a current of 2. So um uh how did the current change? Seems like okay, so this current thing here is weird. I don't know why it's the 0 here, but I can see that the resistance. Let me see. Selected a voltage and closed the switch so current flowed through the circuit, raising the wire's temperature T. The values in table 1 were measured for 5 trials with different wire temperatures. Note the initial value of R, the circuit's resistance, was measured at a temperature of 293 Kelvin with an ohm meter. The other values of R resistance were calculated from the values of V and L. Um, so I think, yeah, I'm unsure of this, like these values, but it seems like the resistance from 293 to 673 goes up by 3 times, right? And if this is held constant and the resistance goes up by a factor of 3, my guess would be that the current should go down by a factor of 3, perhaps. And so I guess
Mm.
this isn't really like it's a, I guess, smaller. I mean, well, hmm. Okay, so I mean, if from this we can at least say that the current should decrease, right?
Mm-hmm. Yes.
So, and I guess only one choice says that, but I'm wondering
I
why.
understand where, like, I would have looked for something that it like includes 2,
Mhm.
but it's not increasing from 2. So I guess they're all like Oh, I'm not sure. I'm really confused by it now that I'm looking at it. I genuinely don't know what provoked me to pick D. I don't like that it says remain constant because it increases to what I would have liked to see here, but
Uh-huh.
I must have just like
I think okay, so I think it's um so they're saying during trial 5 that they heated it up from 293 to
Mhm.
673, but they are saying trial 5. So I think these values are the ones that we have to use, not any of these over here.
Yeah.
So I think that can help us out because we have 28 volts is equal to um 2 amps times the whatever 14 resistance or ohms rather, and that's at 673. So now if the temperature was okay, they also say that current flow when it flows through the circuit, it raises the temperature. So current would be proportional to temperature, I believe. Um, so I think that, well, actually, wait, temperature, okay, current flows through, okay, so if the temperature increases, current flowed through, other values are decreased from 4.6 to 2. Okay, so let's just try this. This is equal to this times maybe 4 ohms. That doesn't work. Let's see. All right, so okay, so resistance, or rather, I'm gonna look at this completely fresh. So okay, as temperature increases here, resistance increases. Temperature is proportional to resistance.
Yeah.
Um, and if it's V equals IR, and this does not change, but we're increasing the resistance, we should see a decrease in current.
Mm-hmm.
And now it wasn't like the 3 times or the oh wait, no, sorry. So okay, maybe not the 3 times distant difference there, but here this goes from 300 to like, I guess it's like, let's see, 300 and then maybe like 700. So like double, a little bit double.
I
So
don't understand why this one's so confusing and I somehow managed to get it right.
I think you were able to maybe, so like what I can see just so far that is definitive, because the values here are not giving me like the exact answers, but what I do see is that temperature goes up with resistance, and we see that resistance, if voltage is held constant and we're increasing resistance, which we are, we must decrease current. So I can tell you at the very least that it can't be constant, it can't be increased. It'll have to be a decrease. But I was just trying to figure out like by what amount. So like this would be, let me just do 7/3. That'll be easier. 3 goes into 7 twice with a remainder 1, which is 1/3, which is 2.3. So if the temperature goes up by a factor of 2.3, 2 times 2.3 would be 4.6. There we go. Got it. Got it. So okay.
I'm so confused.
So okay. This is how to approach this. So
Okay.
figure everything out again. So we're heating this wire from 293 to 673, and we're keeping the voltage the same. So if we're heating this, we see that the resistance is increasing. And even if we didn't have a table, we should know that resistance is like that friction that causes heat to be released or coming out of the resistor. So yeah, so temperature proportional to resistance, and V is equal to IR, and V is held constant. So if we're increasing resistance, we must decrease current. So right away, we know that our answer must involve decrease. Now, what if they gave us more than one choice with decrease? How do we figure out that exact amount? Now, I guess what I first, 14 divided by 4. This is 3, remainder 1/2, 3.5. And that didn't work. So how about this? This goes up by that factor of 2.3, and then that works. So
Okay.
so first figure out if it's increasing, decreasing, or constant, and we know it's decreasing. And then I tried the resistance values, and I get like that it goes up by a factor of 3.5, but the temperature goes up by a factor of 2.3, and that 2.3 using that value will give us the.
But this just feels like, can I see what they're saying?
Yep.
So yeah, the 2.3. Okay. This one is so difficult. Okay, fine.
No, you got it. You know, on the test, you probably determined that, the current would be a decrease, and that's probably why you went with D.
You think, and I wouldn't remember how I went through it.
It's a little, yeah, it's like I don't remember, like, and I see these tests like a million times. So,
Okay.
but
All right. So this one.
oh, this question sucks. So yeah, this is like, I remember this being pretty hard. Okay. So like, yeah, let's check out the stuff
Passage
here.
or what?
Down left, you can go down. So, okay, they're labeling this over here and they're labeling this. And we get this thing over here. So my guess is that what happens is, I think this thing gets maybe like deprotonated to give it a negative charge, which can then attack here.
Okay.
So now, so here, so this is green. This is going to be blue, right? And then, so the green one is attacking. So the green one is making that new bond. Let's see. So the green one is attacking a carbonyl. So it's going to be this one. It's going to be attached to that carbonyl, I believe, if I'm doing this right. Then the blue one is over here. Maybe it's that one. But anyway,
What
at
are
least,
the,
yep.
so the acetyl-CoA reaction,
Yeah, when it hits
what
that,
are the carbon? Wait, I remember how I did this.
Mhm.
Or no, I don't actually. But Wait, what kind of a carbon is it looking for? Because shouldn't this be one?
Let's see. So yeah, so this is just I guess compound 2 getting phosphorylate, or let's see, carbon 14 labeled methylonic acid, compound 2, produced from 14 carbon labeled acetyl-CoA, reactions 1 through 3, is converted in vivo into isopentenyl pyrophosphate, compound 3. What is the expected C14 labeling pattern found in isopentenyl phosphate produced this way? Labeled carbon atoms should be found at. So let me see here. So we got this negative charge with the CoA, and then got another one of these with the CoA, and then this can attack here. This would get push that there. So this would be O minus S CoA, and then a this thing over here as CoA, and then this comes back, this breaks off to give you this, this, CoA, and so this one, okay, this one, so when this attacks that, it will be like this. It would be and I you would we would have this comes back and kicks this off to get that. Now, since we're kicking off like the CoA part of this molecule, the CoA part that remains here will be from this molecule. So that will mean that let's drop down. There. So we can leave these here, and then we're taking this and we're adding another one of these. And then I believe that should add to one of these CH3. Okay, now I want to use pink. So I believe this is going to attack one of these carbonyls. And so it's going to be, and it's going to remove, let's see. Okay, I think this one would be that one. So that, and maybe that, then maybe that, and then we get this. And so over here can be this one here, this one there, and then this one I think will be here.
This is a mean question.
I know. So Yeah, I think this would be a good question to like make a guess on, flag, move on. And even if you spend time like, extra, if you have extra time to go back over the flagged ones, this is still probably going to take so long that it's not even really worth it. Uh,
Yeah.
so
All right.
yeah.
How are we doing time-wise? How many more can we do?
Oh yeah, let's do like maybe like one more, one or two more.
Right,
Finish
so
that 8:30 or whatever. Um, in equilibrium with compound X in aqueous solution, which is the structure of compound X. Did they mention anything about compound X?
no.
Compound.
It exists in equilibrium. So Malvio, where is it? Malevolent car reaction 3. This one.
This is in. Oh, okay. It could be a ring closure.
That's what I thought.
Mm-hmm.
And I put C, but they're saying the correct answer is A. That it's without this like tail here.
Okay. Let's see. Okay. Well, all right. So six-membered rings, what they say here is true. They're going to be preferred because they have less ring strain, and that's uh, going to be the most stable type of ring that's formed. So I would eliminate C, and let me look at D and D. Gotta get rid of those. And so it's going to be one of these. And let's see, how are these different? One has a
The
carbon,
double bond that was here.
and then one has just the hydroxyl group. And so two hydroxyl groups, and then one carbonyl group. And since it'll be the hydroxyl that attacks the carbonyl, um, 1, 2, 3, 4, 5, and then it makes a bond, making it a six-membered ring. So this is going to be part of the ring, and it will move that over. This will come back, reform that double bond, and kick this guy out. So this oxygen hydroxyl is going to be attached to the carbonyl, or attached to the carbonyl carbon, and that's the carbonyl carbon here. And that's pretty much, yeah, that's pretty much it. The CH2OH are still here. So yeah.
Finally, I got something right.
Oh yeah. Yep. The IR spectra with the 1700 being, and that these are like the most common ones you'll see too, like carbonyl group, right?
Just went over this like
Hmm.
recently, so
Hmm.
something stuck.
Yeah. So that's the carbonyl group. This, yeah, the 3 whatever is the OH group. 15V.
This one I don't remember.
Yeah, me neither.
Okay.
But apparently it's not in what we're looking for, so yeah. Single isomer is formed in reaction 2. Um, okay. Yeah, I guess, the enzyme is the thing that is doing like the work
Mm-hmm.
here. And enzymes are stereospecific. So that would explain why a single enantiomer stereoisomer formed, because the enzyme is specific to a specific type of, you know,
Yeah.
chiral chiral thing. So
Okay.
yep.
All right, perfect. So that's it.
Let's see. Is there another one for this? Okay. Oh yeah,
Oh,
this.
wow.
Oh, what's up?
Got it right.
Mm-hmm. Yeah. So like,
Also, squalene, when we were going over a different question on this MCAT, for some reason had squalene as a free
yeah,
and
look at it up here. So cholesterol.
would be closed rings. We talked about this, remember? There was a yeah,
So cholesterol is the precursor to the steroid hormones,
right.
and then
I
squalene is the precursor to cholesterol.
I understand. Okay.
Yep. And they're based on, and then terpenes are based on isoprene units, which basically I believe look something like that. So, oh, and then this is, we talked about myopia.
Yeah, converging, diverging
Yep.
lenses. I
Awesome.
remember.
So, okay. Yeah. I would, okay. So, yeah, I guess, so you're taking a test tomorrow?
Yeah, I mean, I have to. I didn't take one this weekend. I
Okay.
just thought I would break it apart a little bit better since I'm doing one tomorrow, and then we said Thursday. I think I'm doing another one, or maybe next weekend.
Yeah, it could be on the Saturday. If you're doing one tomorrow, um, and you're doing it in one sitting, right?
Yeah, for sure. I don't have anything tomorrow until we meet at 5. So
Yep. Yep. And then, yeah, the next one you could take like on Saturday or something.
okay,
All
sounds
right,
good.
awesome. Good luck tomorrow. And I guess, wait, I'm still seeing you at 5 tomorrow?
Do you want to cancel tomorrow?
Uh, we could do that, I guess, since you're taking your test. So yeah, I can cancel that.
And then we're meeting on Tuesday, right?
Mm-hmm.
Oh, that's fine.
All right. So good luck tomorrow. And yeah, let me know how you do. And then I'll see you on
Tuesday?
Tuesday at 6 p.m. Eastern. Okay.
All right, bye.
All right. Take care. See ya.